The universe is not a still or silent place. It stretches, evolves, and cools with every passing moment, reshaping itself on scales so vast that human intuition begins to unravel. What we see today, galaxies drifting apart, clusters forming intricate structures, the cosmic microwave background glowing faintly across all of space, is only one frame in an unimaginably long film. We know it's beginning with surprising clarity, a hot, dense, expanding fireball that marked the birth of time and space. But its future remains one of the deepest mysteries in modern physics. To understand where the universe is heading, we must look at the forces that sculpt its destiny. Gravity, the ancient architect, pulls matter inward, trying to gather galaxies and stars into tighter formations. Dark energy, a mysterious and invisible pressure, pushes the cosmos outward, accelerating its expansion at an ever-increasing pace. And woven into both is the curvature of space-time itself, the geometric stage on which the entire cosmic drama unfolds. Whether the universe bends open like an infinite saddle, closes in a loop, or remains nearly flat determines how the story might end. The fate of everything, every star, every galaxy, every atom that has ever existed, depends on the delicate balance of these forces. If expansion wins, the cosmos may drift toward eternal darkness. If gravity prevails, everything might collapse back to a single point. And if quantum physics plays its silent hand, the end could come suddenly, without warning, in ways that rewrite the very laws of nature. Every light that shines must someday fade. But how will the final chapter of cosmic history be written? Will the universe freeze, collapse, tear itself apart, reboot, or quietly dissolve into quantum nothingness? In this video, we will explore 5 of the most scientifically grounded scenarios for how the universe could ultimately end, each one born from the equations of modern cosmology, each one stranger than anything imagined in myth or fiction. If nothing in the laws of physics changes, the universe is moving toward a quiet and inevitable conclusion. This fate is called heat death, not because the universe becomes hotter, but because it reaches a state where no useful energy remains to drive motion, create stars, or sustain structure. It is the ultimate exhaustion of cosmic potential. The path to heat death begins with dark energy, the invisible force that accelerates the expansion of the universe. As space stretches faster and faster, galaxies drift apart at increasing speeds. Already, distant galaxies recede so rapidly that their light will never reach us. Over billions of years, this isolation deepens. The night sky, now filled with stars and nebulae, slowly empties. One by one, galaxies slip beyond each other's cosmic horizons, leaving every island of matter alone in an ever-expanding ocean of darkness. Inside these isolated remnants, the formation of new stars gradually ceases. Star formation requires cold molecular gas, but gas is a finite resource. With time, it becomes locked inside long-lived stars or heated and dispersed by supernovae. Entire galaxies age like dying embers. The massive blue stars burn out first, then sun-like stars, then even the faint red dwarfs that can shine for trillions of years. Eventually, no new stars can ignite. Light fades from the cosmos. As stellar remnants accumulate, the universe becomes a graveyard of white dwarfs, neutron stars, and black holes. But even these remnants are not eternal. Over unimaginable time spans, far beyond 10 to the power of 1 years, even black holes begin to evaporate through Hawking radiation, releasing their mass into faint, ghostly photons. One by one, the last structures collapse into nothingness, leaving only thin radiation permeating the void. This is the universe approaching maximum entropy, a state where all energy is uniformly distributed, and no gradients remain to power motion or change. Temperature differences vanish. Gravity no longer sculpts galaxies or stars. Physics itself becomes quiet. The universe has not ended in a fiery explosion or a catastrophic collapse. Instead, it has simply run out of ways to do anything. The final stage is a cosmos of near-absolute zero, where the fabric of space is dark, empty, and silent. Time continues, but nothing happens. No light, no heat, no stars, no galaxies. Only a thin mist of low-energy photons drifting eternally through infinite darkness. Heat death is not dramatic, it is a long, fading sigh. Not destruction, but exhaustion. Not an end of violence, but an end of possibility. The universe does not die in fire, but in infinite, gentle silence. There is a version of the future where the universe does not drift toward eternal coldness, but instead turns around and falls inward, returning to the same kind of fiery, compressed state from which it was born. This scenario is known as the Big Crunch, a cosmic reversal in which the expansion of the universe halts, then collapses under its own weight. The path to a big crunch begins with a dramatic change in the balance of cosmic forces. Today, dark energy drives the accelerated expansion of space. But if dark energy weakens over time, or reverses its effect, switching from repulsive to attractive, gravity could once again dominate the cosmos. In such a universe, expansion would gradually slow until, at some distant epoch, it stops entirely. Space itself would reach a moment of stillness. And then, the collapse would begin. As the contraction unfolds, galaxies that once drifted apart begin to move closer. The vast cosmic voids shrink. Distances that took billions of years to stretch begin to compress in the reverse direction, accelerating inward. Over time, gravitational interactions grow stronger. Galaxy clusters merge into titanic structures. Stars collide. Planetary systems destabilize. Temperatures rise as matter is squeezed into ever smaller volumes. Deep into the collapse, the energy density of the universe climbs. Radiation becomes hotter and more intense. Black holes, instead of evaporating, begin to dominate the contracting cosmos. As galaxies crash together, black holes merge into ever larger gravitational monsters, releasing immense outbursts of energy as space-time ripples through gravitational waves. Eventually, the collapse grows so extreme that the universe becomes a seething, incandescent ocean of plasma, hotter than any star, denser than any galactic core. In these final moments, atoms cannot survive. Even the nuclei of atoms are torn apart. Matter dissolves into a primordial soup of quarks and gluons, resembling the first microseconds after the Big Bang but in reverse order. The final stage is a complete gravitational implosion. Space contracts toward a single point, a singularity, where density and temperature rise to infinity. In this vision, the universe ends not with silence but with a catastrophic inward collapse, a brilliant, all-consuming compression of everything that has ever existed. But this may not be the end at all. Some theories of quantum gravity propose that the Big Crunch could trigger a new Big Bang, igniting the birth of a new universe on the other side of the collapse. In this cyclic universe model, expansion and contraction follow one another endlessly, like breaths in a cosmic rhythm. If true, our universe might not be the first. And it might not be the last. The Big Crunch may be a doorway, not a tomb. There is a version of the future in which the universe does not freeze or collapse, but instead tears itself apart. This is the scenario known as the Big Rip, and it unfolds only if dark energy, the mysterious force accelerating the expansion of the cosmos, grows stronger with time. In this hypothetical case, dark energy behaves as phantom energy, a form of pressure so powerful that it overwhelms every force holding the universe together. Today, dark energy pushes galaxies apart. But in the Big Rip scenario, this repulsive force becomes increasingly dominant, accelerating faster than gravity can counteract. As the expansion rate skyrockets, the distances between galaxy clusters grow not merely steadily, but exponentially. Over billions of years, all galaxies outside the local group slip away beyond the cosmic horizon, leaving every region of the universe isolated. Eventually, the expansion becomes so violent that even galaxies themselves can no longer resist it. The Milky Way, Andromeda, and all surrounding structures are pulled apart, their stars drifting into intergalactic space. The same fate awaits individual star systems. The gravitational bonds that hold planets in orbit begin to break. Worlds detach from their suns. Moons lose their orbits and wander into the darkness. As the Big Rip accelerates, the scale of destruction increases. In the final minutes before the end, the expansion becomes powerful enough to counteract the internal forces of stars. They are torn apart from the inside, their nuclear furnaces extinguished in seconds. Soon after, planetary matter and even the densest stellar remnants begin to disintegrate. But the most dramatic moment occurs in the final fractions of a second. When the repulsive force of phantom energy becomes overwhelmingly strong, atoms themselves can no longer stay together. Electrons are ripped from nuclei. Protons and neutrons are pulled apart. The very fabric of matter comes undone. And with it, the fabric of space-time follows. Distances stretch infinitely in an instant, tearing the geometry of the universe into a final catastrophic expansion that outpaces all physical processes. No stars, no atoms, no space-time. The universe ends not with silence, but with complete disassembly, a disintegration of everything down to its most fundamental components. The Big Rip is the most dramatic and violent of all cosmic endings, a scenario in which structure cannot survive on any scale. It is the ultimate triumph of expansion over gravity, over atoms, over the very idea of space itself. If dark energy grows stronger, the universe will not die. It will be torn apart. Among all possible futures of the universe, none is as unsettling, or as elegant, as vacuum decay. Unlike cosmic freezes or gravitational collapses, this scenario does not rely on stars, galaxies, or dark energy. Instead, it concerns the most fundamental fabric of reality, the quantum vacuum itself. In quantum field theory, what we call empty space is not truly empty. It is the lowest energy state of all the fields that permeate the universe, or at least we think it is. There is a possibility that the vacuum we live in is not the true ground state, but a metastable state, like a ball resting in a shallow valley instead of the deepest one. Such a configuration can persist for billions of years, but it is not truly stable. Somewhere, far deeper in the landscape of quantum fields, there might exist a true vacuum with even lower energy. If such a deeper state exists, then reality as we know it is balanced on borrowed time. Vacuum decay could begin in the simplest, quietest way imaginable, through a quantum fluctuation. In an instant, in some distant region of space, a tiny bubble of true vacuum could form. This bubble represents a new version of physics, with different constants, different particle masses, even different laws. Within this region, matter as we know it cannot survive. The forces that bind atoms, molecules, and even nuclei together may no longer exist in the same way. Once formed, this bubble of true vacuum would expand outward at the speed of light, devouring the false vacuum we inhabit. No signal could outrun it. No warning would arrive beforehand. For any observer, the end of the universe would happen faster than thought itself, a seamless transition from existence to non-existence. Inside the expanding bubble, physical laws reorganize. The strength of the electromagnetic force may change. Quarks might not bind into protons. Gravity might behave differently. The Higgs field might settle into a new configuration, altering the masses of all particles. In such a universe, atoms as we understand them would be impossible. Stars would never ignite. Chemistry would vanish. It is not an explosion of matter, it is a rewriting of reality. From the outside, the advancing bubble would appear as a perfectly smooth wall of nothingness, an expanding frontier where the old universe ceases and a new one begins. There would be no fire, no shockwave, no visible destruction, only instantaneous transformation. And inside the bubble, the rearranged laws of nature would determine whether a new cosmos could form or whether everything dissolves into a featureless vacuum state. Vacuum decay is not a violent apocalypse. It is an upgrade of the universe's operating system, one that simply does not preserve the previous version. It is the ultimate expression of quantum instability, silent, sudden, completely unstoppable. The universe would not end in fire or ice, but in an instantaneous shift to a new reality, a cosmic reboot written into the mathematics of quantum fields. Not all endings are truly endings. In some of the boldest theories of modern physics, the death of one universe becomes the birth cry of another. This final scenario, quantum rebirth, imagines a cosmos that refuses to vanish, choosing instead to transform itself in a cycle of collapse and renewal. Certain models of quantum gravity, such as loop quantum gravity and specific frameworks within string theory, propose that space-time cannot compress infinitely. At extremely small scales, the geometry of space becomes quantized. It resists being squeezed beyond a fundamental limit, much like matter resists compression inside a neutron star. If the universe ever collapses into a big crunch, these quantum effects might create a bounce, preventing a true singularity. Instead of ending, space-time could recoil and expand again, igniting a new Big Bang. In this vision, our universe is part of a larger cosmic rhythm, an endless sequence of expansions and contractions, each one giving rise to a new set of physical constants, new structures, new galaxies, and perhaps new forms of life. Every cosmic era becomes a chapter in an infinite book, and we occupy only a single page. The fate of the universe is not a fading whisper, but a heartbeat. Another interpretation, equally breathtaking, suggests that universes may bud off from black holes. According to this idea, when matter collapses into a singularity inside a black hole, it does not merely disappear. Instead, the extreme compression could trigger a new expansion on the other side, forming an entirely separate universe with its own timeline. In this picture, black holes become cosmic wombs, each one potentially containing a universe of its own. And by extension, our own universe may have begun inside the collapse of a black hole in a parent cosmos, a descendant of a previous reality. Quantum rebirth transforms the end of everything into a beginning. It imagines a cosmos that behaves less like a story with a final chapter and more like a living organism, constantly renewing, constantly becoming. The laws of physics that shaped our stars, our elements, our bodies may be the inherited traits of universes long gone, passed down through gravitational collapse and quantum geometry. Perhaps nothing in the universe is ever truly lost. Perhaps every collapse is a doorway, and perhaps our universe, with all its light and darkness, is simply one bloom in an eternal cosmic garden. Even with all our models and measurements, the future of the universe remains an open question. The cosmos is governed by laws we understand only partially, and the forces shaping its destiny may be far more dynamic than we can currently imagine. Beyond the 5 classical scenarios, physicists consider a range of additional possibilities, subtle, speculative, but rooted in real scientific uncertainty. One idea is that dark energy might not be constant. It could evolve over time, slowly changing its strength or even reversing its effect. A universe with a weakening dark energy might slow its expansion, stabilizing into a quiet equilibrium. A universe with strengthening dark energy could accelerate endlessly, or drift toward behavior unlike any model we currently predict. Every slight change in this mysterious force reshapes the cosmic timeline. Another factor is dark matter, which scaffolds the cosmic web and anchors galaxies in place. Its long-term stability is not fully understood. If dark matter decays over trillions of years, the gravitational binding of galaxies could unravel gradually. Structures would dissolve from within, not through expansion but through the quiet disappearance of the very particles holding them together. Conversely, if dark matter interacts through forces we have not yet discovered, the future might contain phases of cosmic evolution we cannot yet imagine. Some physicists speculate about entirely new forces or particles that may emerge only at extremely low densities or extremely long timescales, conditions that do not exist yet but will arise in the distant future. The universe could undergo phase transitions, subtle shifts in its underlying physics, just as water turns to ice or steam. A new force might dominate, a new particle might appear, or the vacuum itself might transform in a way that guides the universe toward an unexpected fate. Finally, the very shape and topology of the universe may hide surprises. If space wraps around itself in higher dimensional ways we cannot detect, the distant future could reveal behaviors tied to this hidden geometry. The universe might be finite but unbounded, looping in ways we do not yet perceive. Or it might possess structures, tunnels, twists, or compact dimensions that only become dynamically important as the cosmos stretches through unimaginable epochs. These possibilities remind us that the story of the universe is not fixed. It is a question still being written, shaped by forces we have yet to uncover, guided by laws that may evolve, and held together by mysteries deeper than time. The future is not a single path, it is a landscape of cosmic dreams, waiting for physics to catch up. In the end, every theory we craft must bow to one truth: we do not yet understand the force that governs the universe's destiny. Dark energy, the mysterious pressure-driving cosmic expansion, is still a shadow on the edge of physics. We can measure its effects, but its nature remains unknown. Is it constant? Is it evolving? Is it a field, a property of space, or something more fundamental than either? Until we answer that question, the future of the cosmos remains open. For now, the evidence points toward heat death, a slow fading into darkness as galaxies drift apart and energy becomes too thin to sustain structure. It is the scenario most consistent with what we see today: accelerating expansion, cooling space, and a universe that seems to be emptying itself of motion and light. But science is not prophecy. The other endings, collapse, rupture, rebirth, decay, still stand as real possibilities, each supported by ideas that emerge from modern physics. The cosmos may reverse course. It may tear itself apart. It may tunnel into a new vacuum. It may even begin again. And so the final note is not certainty, but humility. The universe may end with a scream, a catastrophic tearing of space-time. It may end with a whisper, a slow dimming into eternal quiet. Or it may end with a birth, a new cosmos rising from the ashes of the old. But its story does not conclude here. Because as long as we look upward, question boldly, and listen to the silent language of the stars, the universe is still revealing itself, and we are still learning how to read it.